I am Dr. Mrs. Wankhede, Head of the Department of Applied Physics, KDK College of Engineering. Today I am going to deliver lecture on optical fiber. This is first lecture on optical fiber, that is unit number 2 in our syllabus. Content of the optical fiber unit are: first we'll cover introduction, then principle of working of an optical fiber, its structure, classification based on material, refractive index, profile, and number of modes. Then we will discuss acceptance angle, derivation of acceptance angle, then how it is related with numerical aperture, then attenuation, dispersion, and application of optical fiber as sensors, and then light detector. So what is optical fiber? That we'll see first. So optical fiber is a technology which is called fiber optics. It is used widely in telecommunications network, in medical field as sensors, and in military field too. The technology came in 1880 when Alexander Graham Bell developed photophone, which was used to transmit speech on a beam of light. In 1954, Van Hill and Harold Hopkins discovered cladding covered optical fiber cables. In 1960, it came in glass clad fiber. Charles Quenkow is known the father of fiber optics communication for his discovery of inventing specific glass fibers to be used in high-speed communication. The first optical fiber cable was laid across Pacific Ocean in 1996. Indian connection to fiber optics: Narinder Singh Kapani, an Indian-American physicist, is credited for coining of term fiber optics and is also considered the father of fiber optics. He was awarded India's second highest civilian award, the Padma Vibhushan, posthumously in 2021. He worked with Hopkins to develop optical fibers capable of good image transmission. His research work includes fiber optics, lasers, biomedical instrumentation, and solar energy. Then what is optical fiber? It is a thin, transparent, cylindrical conduit or waveguide. It is made up of transparent plastic or glass. It guides or transports light across its length. It is as thin as human hair. Then optical fiber basically consists of three main components, that is core, cladding, and sheath. Each one of above has some specific function. These are some examples of optical fiber where it is used. So then we'll see the structure of optical fiber, how it is made up of. So there are three main regions in optical fiber. Core is the innermost light guiding region. It is of 8 to 60 micrometer in diameter. Then cladding, that is the coaxial middle region having refractive index less than core. It helps to guide the light into the core region of 50 to 125 micrometer. Then buffer coating, it is a thin buffer coating or sheath. So it is outermost region. It protects the core and cladding from any type of damage, pollutants, cuts, abrasions, moisture, and its diameter is of about 250 to 900 micrometer. Cladding diameter is 50 to 125 micrometer. Then what is the principle of working of optical fiber? So when light travels from the optically denser medium to rarer medium, it gets bent away from the north. And as the angle of incidence increases, the refracted ray bends more and more. At some angle of incidence, that is critical angle, the ray just glide along the denser to rarer boundary and the angle of refraction becomes 90 degree. So if the angle of incidence is greater than critical angle of incidence, light ray gets totally internally reflected. It gets reflected in the same medium, denser medium. Okay. So what is total internal reflection? So when a ray of light travels from denser medium to rarer medium at an angle of incidence greater than critical angle of incidence, then the ray is reflected back in the same denser medium. This is known as total internal reflection. Then what is critical angle of incidence? So that is the angle of incidence in denser medium for which the value of angle of refraction becomes 90 degree is known as critical angle, that is phi c. Its symbol is phi c. So as we know Snell's law of refraction, so that is sin I upon sin r is equal to refractive index n2 upon n1. That is the n2 is the refractive index of cladding and that is in rarer medium, and n1 is refractive index of denser medium, okay, that is core. So when angle of incidence I becomes critical angle of incidence phi c, then angle R becomes 90 degree angle of. So sin phi c upon sin 90 is equal to n2 by n1, or sin phi c is equal to n2 upon n1 because sin 90 is 1. So its formula for critical angle of incidence is phi c is equal to sine inverse of n2 by n1. So this is the important formula on which the problems can be asked. Then light propagation, how the light is propagated through the optical fiber. So for total internal reflection through an optical fiber, conditions to be satisfied are refractive index of core, that is n1, should be greater than refractive index of cladding, and light should be injected into the fiber in such a way that angle of incidence at core cladding boundary should be greater than critical angle of incidence, that is phi c. That means phi should be greater than phi c, then only there will be total internal reflection. The main function of optical fiber is to accept and transmit as much as light as possible from the source. This is known as light gathering ability. So numerical aperture determines the light gathering ability. Now following are the factors which decide the performance and light gathering ability of the fiber. So number one is acceptance angle, then acceptance cone, and fractional refractive index change and numerical aperture. So we'll see first acceptance angle, its derivation. So when here initially the light ray is incident at an angle theta I in the outer medium with the axis of the fiber. Let n naught be the refractive index of launching medium and theta r be the angle of refraction, and phi be the angle of incidence at the core to cladding boundary. At the core to cladding boundary, and let N1 be the refractive index of core and N2 be the refractive index of cladding. Okay, so here this is cladding, this is core, this region. Okay, so by Snell's law of refraction, this sin theta I upon sin theta R is equal to N1. N1 is the refractive index of core upon N naught. N naught, that is in outer, refractive index of outer medium. So sin theta I is equal to N1 upon N naught into sin theta R. Since theta R is equal to, from this diagram you see, angle A is theta R, that is theta R plus this is 90 degree angle C in this triangle ABC. Angle A is theta R, angle C is 90 plus angle phi. So that is total is 180. So theta R will be equal to 180 minus 90 minus phi. So that will become 90 minus phi. So sin theta R is equal to sin 90 minus phi is equal to cos phi. Now we know this sin theta I is equal to N1 upon N naught, so cos phi. So theta I, now we will apply the condition, if if theta I is equal to theta I maximum, then phi will be equal to phi c. So theta I maximum, sin theta I maximum is equal to N1 upon N naught into cos phi c. Now as we know, sin phi c is equal to N2 by N1, because sin phi c upon sin 90 is equal to N2 by N1. So cos phi c is equal to square root of 1 minus sin square phi c, and 1 minus sin square phi c means 1 minus square root of n2 square upon n1 square. So it will become, after solving, square root of n1 square minus n2 square upon n1. So sin theta I maximum is equal to this n1 upon n naught into square root of n1 square minus n2 square upon n1. So that is equal to n1 n1 cancel, and it will become square root of n1 square minus n2 square upon n naught. So if we take this theta I maximum is equal to theta naught, then this equation will become sin theta naught is equal to square root of n1 square minus n2 square upon n naught. So theta naught is equal to sin inverse square root of n1 square minus n2 square upon n naught. So for, if outer medium is air medium, then for air medium n naught, that is the refractive index of air medium, is 1. So sin theta naught is equal to square root of n1 square minus n2 square, where theta naught is called acceptance angle. So how will you define acceptance angle? It is the maximum angle of incidence that a light ray can have with the axis of the fiber, for which light undergoes total internal reflection within a fiber. It's called acceptance angle, and it is denoted by theta naught is equal to sin inverse of square root of n1 square minus n2 square. Okay. What is acceptance cone? The light rays, this is contained within this cone having full angle to theta naught with the axis, are all accepted and transmitted along the fiber. So this cone is known as acceptance cone. So 2 theta naught is equal to twice of sin inverse square root of n1 square minus n2 square. Then what is fractional refractive index change? The fractional difference between the refractive indices of core and cladding is known as fractional refractive index change. It is denoted by delta. So delta is equal to n1 minus n2 upon n1. The next term we'll see what is numerical aperture. So it is a measure of the light gathering ability of the fiber. Its value depends on refractive indices of core and cladding. So larger the value of numerical aperture, larger is light gathering ability of the fiber. So numerical aperture is defined as the sine of acceptance angle. So numerical aperture is equal to sine theta naught is equal to square root of n1 square minus n2 square upon n naught. Therefore, numerical aperture is equal to sine theta naught is equal to square root of n1 square minus n2. Okay. So where that n naught is equal to 1 for air medium. So from this equation, we are seeing that numerical aperture depends upon acceptance angle, and which in turn depends upon the refractive indices of core and cladding. So its value is in the range from 0.13 to 0.50.